Last episode, we designed the graph behind a social network. This episode, we designed the thing behind a search engine that gets hit 4,000 times a second. The key value store. The KV store. You search a word. How do the results come back so fast? Because in front of it sits a giant cache. But this cache won't fit on a single machine. Today, I'll actually run it for you. How to split it, how to add machines without moving everything, how to not lose anything when one dies. The star. Consistent hashing. First, the math.
10 million users, 10 billion queries a month, 4,000 a second. Each result is 270 bytes, all unique. That's 2.7 terabytes a month.
Why do we even need a cache?
Memory is 250 microseconds. SSD is 4 times slower, disk 80 times slower.
That is the entire reason a cache exists. First, the cache itself. It fills up, so it has to evict. Evict which one? LRU. Evict the one unused the longest. Search traffic is skewed. A few hot terms take the lion's share.
LRU keeps the hot ones, hitting 65%. FIFO evicts purely by insertion order, hitting 60%. Same size, FIFO treats hot entries as old and evicts them too, hammering the backend 1.14 times as hard.
How does LRU pull off O of 1? A hash table, O of 1 lookup. A doubly-linked list, move to the head on a hit, drop the tail on overflow. That's the classic structure. Now the cache doesn't fit, so we split it across multiple machines. The most intuitive way. Machine equals hash of the key, mod n. Where's the problem? I add one machine, n goes from 10 to 11.
Out of 100,000 keys, 91,000 switch servers. 91% moving house.
What does that mean? The cache collapses. Every request slams the backend in the same second. Thundering herd. One scale-up, one storm. Consistent hashing, a different approach. Put the nodes on a hash ring. A key goes clockwise to find the next node.
Add one machine, and it only touches the arc between it and its predecessor. Only 8.3% move, less than a tenth.
10 times fewer. The rest hit as usual.
Then add virtual nodes. Each machine puts 150 points on the ring, and the load imbalance goes from 21 times down to 1.22 times.
The key to sharding isn't how to split it. It's don't move everything when you add or remove machines. This is the star. But one copy isn't enough. One machine dies, and its share of the keys is just gone.
Out of 100,000, we lose more than 9,000.
Store every key on the next 3 nodes clockwise on the ring.
One machine dies, the other 2 copies keep serving. Lost. 0. The death is invisible to the reader.
But with multiple copies, how do you guarantee you read the freshest one? Quorum.
A write needs 2 replicas to confirm. A read needs 2 to answer, as long as the write set plus the read set is greater than the total number of replicas.
The read set and the write set must overlap. What you read is guaranteed to be the latest write. Tune these 2 numbers and you slide between consistency and availability. This is the cap trade-off from that episode, landing on every single key. So where does AI touch this? The search KV grows a second index. Exact KV, give it a key, get the value, O of 1, perfect. But search also asks for results that mean the same thing. I search low-cost airline Nippon. All synonyms, not one of the original words.
Keyword search. Out of 5, 0 hits. Vector index, ANN, by meaning. 3 out of 5, pulling back budget airfare and affordable plane tickets.
A modern search KV runs both. The inverted index keeps it exact, vectors keep the recall, hybrid retrieval. The 4 questions, plus the honest note.
What it helps with. The vector index adds semantic recall to the KV, hybrid retrieval, inverted plus vector. What it replaces. Pure keyword matching replaced by exact plus semantic. What it changes. One more kind of shard on the ring, one more path in the query, ANN.
And what can't it change? Let me be honest. AI added a new index to the KV, but it didn't change consistent hashing, didn't change LRU, didn't change replicas, didn't change quorum. The skeleton. The vector index, HNSW, itself still has to be sharded and replicated. It's just one more thing hanging on the ring, not a replacement for the ring. The skeleton stays the same, just one more index. Before we wrap, a few pitfalls. 1. Naive hash mod N. Never ship it to production. Adding a machine is suicide. Consistent hashing is the baseline. 2. Don't skimp on virtual nodes. Too few and the load gets lumpy. Some machines work to death, others sitting idle. 3. One replica is the same as none. At least 3, and place them across racks and across availability zones. 4. Misconfigure the quorum, and you either read stale values or can't write at all. Burn it in. Writes plus reads, greater than the total. 5. An absolute hotkey. Not even consistent hashing can save you. A single viral term can crush one node, so you replicate it on its own or put a local cache in front. Let me weld it into one sentence to close. A search engine's KV store is an LRU cache, plus consistent hashing sharding, plus replicas and quorum. Again, parts from the earlier episodes. Cache, sharding, replicas, cap. Bolted together. On top, AI hangs a vector index. But that ring is still the same ring. Next problem. We design Amazon's bestseller ranking. MapReduce time window aggregation. See you.